Hey folks, thank you for coming in. This is our first talk after the lunch break. We'll just get started in a couple of seconds. We are waiting for everyone to join back. All right, so perhaps we'll get started meanwhile other people join. So our next talk is by Aditya Lohiya on deploying ML solutions with low latency in Python. Aditya is currently working as a senior machine learning engineer at Kai's AI. He has provided real-time accurate solutions for multiple use cases in computer vision, and he loves giving back to the community that has really helped him learn. The talk is about we have higher accuracies because of higher latencies that we have been compromising those accuracies. So he's going to talk about a framework that takes care of the latency so you can deploy better algorithms. And we'll be taking all the questions towards the end of the session. You can drop your questions over the Q&A tab. Aditya has shared some reference code and slides in the session feed. Over to you, Aditya.
Thank you, Jatin. Thank you for the wonderful introduction. So I'll be sharing my screen now. I hope it's visible. Okay, all right. Uh, yeah. So thank you, folks, for joining just after lunch. It's an honor to present at PyConf Hyderabad. So today's topic is deploying ML solutions with low latency in Python. I'm Aditya Lohiya. You can find me at my LinkedIn profile and my website. I'll be sharing the slides as mentioned. So let's start. So as the world moves on, with the research in improving accuracies, I'm really sorry. Yeah, sorry. So as the world moves forward with the research in improving accuracies of deep learning algorithms, we face an imminent problem of deploying these algorithms. So if anyone is working in AI in the industry, you might have noticed that there are algorithms like YOLO V5 coming out again and again with improved results, with improved scores, but we lack the architecture to deploy those algorithms on edge. So what do I mean by low latency? So latency is the term that we use to understand the time taken by an algorithm to perform inference on an image. Generally, when we set up an ML pipeline, we have the bottleneck at the model inference stage, wherein the model takes a lot of time to infer from an image or from multiple images if you're giving in a video. So there are multiple methods that the research has used to improve latency. One of it is weight quantization, wherein you reduce the format of the weights. That is, you go from float 32 to float 16 to int8 quantization. That generally improves your latency, but at int8 you might notice some accuracy drops. Then you can use model pruning to prune your models at the end, and then you can reduce the number of parameters as well as the model size, thus helping you to improve the latency. You can use knowledge distillation, and that is a very broad topic that I won't be able to cover. But yeah, its general idea is that you train a smaller network based on the knowledge from a bigger network, and it learns the exact weights of the bigger network. And then comes it the framework based deployment. That's our today's topic. So we'll be focusing on two frameworks that are TensorRT and Deepstream. So what is TensorRT? So TensorRT is an SDK by NVIDIA, which is focused on high performance deep learning inference. It includes a deep learning optimizer and a runtime. It is focused on deploying your solutions with low latency and high throughput, and it supports both APIs, Python and C++. So in TensorRT, you can convert your model's weights from multiple frameworks as mentioned, that are TensorFlow, PyTorch, MXNet, Theano, Caffe, and there are multiple parsers available for converting those weights to TensorRT. So generally what TensorRT does is you take your trained neural network in any framework, you now have to create an inference engine in TensorRT. So the TensorRT runs an optimizer on top of your trained neural network. It does the following tasks, that is precision calibration, layer tensor fusion, kernel auto-tuning, multi-stream execution, and dynamic tensor memory. Now after employing these tasks, it generally gives you an inference engine that you can serialize to the disk, or you can use that inference engine when you are deploying the algorithm. So what are the optimizations that TensorRT does? So when you talk about weight and activation precision calibration, it's as I mentioned before, you use float 32 weights to again generate float 16 and intent weights while preserving your accuracy. Now it is a little heavier in computation during conversion to intent because you have to provide a data set and you have to do quantization on your own. Then next is layer and tensor fusion. So wherein your layers based on the architecture of the network, TensorRT focuses on combining those layers and tensors into a single kernel. Now that can really help your model do inference in very short amount of time compared to before. Then it employs kernel auto tuning. So basically what it does is it selects best data layers and algorithms based on your target CPU platform. So one specific thing about TensorRT is that you have to generate your inference engines based on different GPUs. That is, if you are using a 1050 Ti platform, you'll have to generate your engine on a 1050 Ti GPU. Similarly for 2080 Ti's or nowadays 3080s. Then it does dynamic tensor memory, wherein minimizes the memory footprint and it focuses on reusing the memory that the tensors use for calculation efficiently. There's a whole lot of resources available on understanding that specific aspect. And then because of NVIDIA's capabilities to improve your multi-streaming, it focuses on processing multiple input streams in parallel while you are doing inferences. So then how does it work? So TensorRT converts your, like you'll have, so I'll focus on conversion from a PyTorch based model, but you can do so from any framework. There are multiple options available. You can even declare the network definition using the network definition API of TensorRT. You can basically load your weights from any framework upon there. So for a PyTorch model, what you can generally do is you can convert that PyTorch model into ONNX, and ONNX is a framework which is employed by the industry to convert different frameworks, or also run your models in real time inference. And then you can go on to convert that ONNX model to TensorRT. So after that, what happens is you apply optimization, that is TensorRT uses the optimizations, but you'll have to specify those, and then it generates an engine. And after that you can serialize it, or you can generate the engine real time based on your capabilities and based on your architecture of the pipeline, and then you can perform an inference of the GPU. So at this moment I would like to show you guys a code that you can use to actually convert your PyTorch model to TensorRT. However, I won't be able to run it because it takes quite a while to run it, and I don't think I'll have the time to actually demo this out. So I'm using a open source network known as Retina Phase. It is a PyTorch based state-of-the-art phase detection algorithm. I'm using its weights based on MobileNet right now. You can also use its ResNet weights. So basically what you have to do is you can employ the general PyTorch ONNX library, and you can directly export it in a single line. You just have to load the module, you have to convert it into eval, and then you can export it based on the inputs and output statements. Now this saves a ONNX weight. Now what you have to do after this is you have to convert it into TensorRT. So basically you can specify ONNX weights, and then what a TensorRT does is you have to create a TensorRT builder. You have to create a network definition API, and you have to create an instance of the ONNX parser. You can load the ONNX weights using this part of code. Now you have to feed that ONNX weights into your TensorRT engine that you have declared over here, builder and network definition API. However, you can use multiple things. Either you can simply use dynamic optimizations profile that will help you in creating a TensorRT engine. We can take in shapes dynamically. By default, TensorRT uses static shapes, that is, you'll have to feed in the shape for the input layer. I have done this dynamically because Retina Face is trained on dynamic image sizes. So you can feed input image sizes from 32 by 64 to 4K images. And that is really awesome because, I mean, 4K images processing on 2080 GPU is really hard, that I have learned from my industry experience. So after this, you can add the optimization profile to your TensorRT engine, and then you can build your engine. Now it takes about 10 to 15 minutes based on the network to build that engine. But once you have done that, you can simply go ahead and serialize the engine to the disk. Now this is simply how you can convert the engine to TensorRT. And for inferencing, it's the same thing. Right now, I'm using the pre-processing steps and post-processing steps of PyTorch itself, and I just convert a tensor and then convert it back after the network outputs. So what you have to do is NVIDIA gives you a common.py file wherein they have all the basic functions that you will require to inference from the engine, and that's really helpful because you don't have to understand the entire framework. Then you can simply go and allocate buffers. Now what allocate buffers means, it because this runs the network on a GPU, and this is like below TensorFlow and PyTorch. So what happens is you'll have to allocate buffers to save the memory, and then you'll have to have instances of those buffers into your code. Then you'll have to copy the images into the input buffers. You'll have to do inference based on the bindings, and then you can get the output from output buffers, and then you can do the post processing. One thing to notice here is that you can set TensorRT workspace size, and that is really helpful because for bigger models. So this here I'm setting a 256 MB workspace size. TensorRT can easily deploy a Retina based network on a 256 MB size, that is the memory consumption of a GPU. However, if required, you can go beyond that. However, TensorRT will only employ the maximum size available or maximum size required to deploy that algorithm. So this code is available on the GitHub link that I've posted before, and you can use that GitHub link to clone and then generate your own weights and try to inference from a retina phase algorithm. Getting back onto the presentation. So as you can see, there are different metrics that I have calculated after running TensorRT on Retina phase. So this is just for TensorRT. So just to inform you, Retina phase Resonate 50 based model, if you run it with the same input shape using PyTorch or TensorFlow, you get an FPS of about 20 on a 2080 GPU. And if you run the Retina Face mobile net on a 2080 GPU using PyTorch or TensorFlow, you will get an FPS of around 40 to 50. Now, after converting the weights to TensorRT, as you can see, I'm not even utilizing the FP16 weight quantization for Resonate 50, and still it gives me an FPS of 81. I can directly correlate the 81 FPS to the low latency, and it's basically simple. You divide 1 second by 81 and you get the latency for each single image. And this is pretty awesome because now you can deploy Retina face with the backend of Resonate 50 on a GTX 1080 on a real-time basis with multiple streaming, with multiple input images and input feeds. And if you look at when you do end-to-end quantization, you get an FPS of about 180, 180 to 190. Now this is again pretty awesome, but you might notice a little 1 to 2% drop in accuracy. I think it's okay to deploy drop in accuracy for such a great FPS. If you look at the matrix for mobile net based retina face, you get a whooping FPS of 400. Now you can deploy this on a Raspberry Pi. I have done it. I have deployed this algorithm on mobile Jetson Nano using TensorRT, and it can simultaneously handle 8 streams alone, a single Jetson Nano. And that is pretty awesome because I work for to develop pipelines in AI City. Now I have again pushed some metrics for YOLO v5, that is the state of the art object detector that is researched and that is published by Ultralytics. Now if you look at the matrix, so YOLO v5s, and it is again, I use GTX 1080 GPU. You can run state of the art object detection at an FPS of 142 on float 16. Now just imagine what you can do with an intet quantization. Intet was a bit harder for this algorithm because I had to again annotate multiple objects and I didn't have like some time to do that. And so as you go downwards, you'll notice an increase in accuracy because these models go on larger. So these are the smaller YOLO v5s, whereas this is the YOLO v5 medium and this is the YOLO v5 large. So if you deploy your v5 large, you can detect any object, even if it's far, like very far and very small in the camera frame at an FPS of 30. And you won't notice this performance if you deploy it using PyTorch. I mean, YOLO V5S running on a GTX 1080 gives you about 2 to 3 FPS with a single batch size. Now, what are the best practices that you can employ for TensorRT? So, as I have mentioned before, you can use mixed precision. That is, you can deploy the weights using float 32, float 16, and int 8. And you don't have to rebuild the engine for during each inference. You can just serialize that engine and then load that engine again to perform inference. And as I mentioned, you can change the workspace size. So in case here I'm using 256 MB for retina phase, but you can go on to employ much bigger sizes for much bigger algorithms, and that would be completely fine. However, TensorRT will only use size required for deploying that algorithm. Things to keep in mind about TensorRT is, so as the engines are generated to a specific machine or a specific GPU, an engine generated in GTX 1080 won't work on a RTX 2080 Ti, and vice versa. So you have to generate engine based on your GPU architecture. And moreover, the installation is quite big and it takes quite a time if you are not utilizing Docker. Now, NVIDIA provides a NGC container for TensorRT. You can just employ that to to convert your algorithm to TensorRT. And there are multiple APIs for conversion. Now, you can use the network definition API, or you can use the UFF parser, the 1NX parser for converting your TensorFlow, PyTorch, MXNet weights to TensorRT. So moving on, what is Deepstream? Now, Deepstream is again an SDK from NVIDIA that is focused on optimizing your entire pipeline and not just the model. So as we talked about model inference times using TensorRT, Deepstream employs TensorRT to again build on the entire pipeline, run that entire pipeline on GPU, and streamline your pipeline to perform inference in a much complicated environments on an edge devices. So it comes with TLS security. You can deploy it on edge as well as connect it to any cloud. And so what Deepstream does is, and what NVIDIA has done is, they have used the GStreamer objects and they have customized those objects to run on GPUs. While they do not use it, they use GStreamer objects generally use CPU. NVIDIA has customized it to run on GPU. And using Deepstream, you can even utilize multiple frameworks on a single deployment pipeline. You can use TensorRT, TensorFlow, PyTorch, all integrated in one pipeline without having to worry about memory consumption. So as we talked about the model inference bottlenecks in TensorRT, as you can see highlighted by the red circle, Deepstream focuses on the entire pipeline. So this is generally an architecture of Deepstream. You use an NVIDIA computing platform, and one thing to notice is TensorRT and Deepstream can only be utilized on an NVIDIA graphics card. So NVIDIA platform generally run CUDA and TensorRT, Triton inference servers and everything on top of those platforms. And then you can use Deepstream to perform multiple things. You can use hardware accelerated plugins. You can use IoT messaging. You can update model based on OT updates. You can create Helm charts that are very common with Kubernetes applications. And then you can finally streamline your application using Python and C++. So this is generally how a Deepstream pipeline will look at. You take in the frame, you can take in the raw video input, and it runs on CPU. Then the Deepstream decodes that using NVIDIA DEC object. Now this is done on the GPU, so it's very fast. Similarly, your image processing will be done on GPU. Your batching will be done on CPU. That is, if you have multiple streams, you have to create a batch to inference from a network. Now, in this part, the DNN part, you can deploy TensorRT, TensorFlow, PyTorch, as I have mentioned before. And then Deepstream even includes tracking, and that is like really important in use cases like AI City. So it comes with an inbuilt tracker that can run on both GPU and CPU. It's your choice. Now you can create visualizations in Deepstream based on the objects, like the output that it returns, and you can display it on screen using GPU after decoding it, and you can simultaneously process those outputs and then send it to different hard-coded environments or hardware architectures using HDMI, SATA, and NVENC. So these are some of the networks that NVIDIA has already trained and optimized for Deepstream. Now, if you see here, you have a Resonate 18, Resonate 34, and these are trained on different datasets that NVIDIA has mentioned on their website. You can go over here and use this link. So these are all converted to int quantization, and you can see the accuracy metrics for all these algorithms. PeopleNet is generally focused on detecting people. Traffic CamNet is generally focused on detecting vehicles, pedestrians, cycles, etc. Dashcam nets are specifically optimized for dashcams that come in police cars, and you have again phase detector using Resonate 18. Now, if you see it, you can see that if you just use Jetson Nano, you'll have quite a lower accuracy. But as you go on using Jetson Xavier and Jetson AZX Xavier using Deepstream, you will get a impressive accuracy of 218, 1200, and also. So I mean, this is quite impressive, and I mean, I love Deepstream because of this. And there are a couple of resources available for TensorRT. I've mentioned all those here. You have Python-based code compilations, and you have C++-based network definition APIs. NVIDIA has a great great collection of blogs and developer guides for converting your models to TensorRT and Deepstream. So I think I've already shared you the code, and I've shared you the presentation. Here's if you have any questions, I'll be happy to answer those. So yeah, so TensorRT. So based on the question from Shankara, does TensorRT reduces the model size when converting the model to float 16? Yes, it does. You often notice that the model size, that is the model size that is saved on the disk, is reduced to half because it saves the model on float 16, unlike other frameworks where you'll have to save the model on float 32 and then convert it to float 16 when you're loading those. So yeah, it reduces the size. How long does it take for object detection in Raspberry Pi? So I mean, it depends on which object detection algorithm you are using, which uh, framework are you using. So if we talk about doing YOLO, using YOLO v5 small using TensorRT, you can expect an FPS of about 30. I mean, it's using YOLO v5 small and on a Raspberry Pi, and I'm talking about the base Raspberry Pi with 1 GB RAM. So but you'll have to integrate the GPU. Question from Priyabrata: what other SBC good for deep learning or computer vision? So I mean, I think you can use Jetsons. You can use Movidius chips that can convert any computer into a deep learning inferencer. There is again a product coming in from Intel. You can use that for optimizing your deep learning pipelines for computer vision, and so I think you can also use Raspberry Pis because of TensorRT. Can we use this for inferencing machine learning models in production? No. NVIDIA has currently limited their support to deep learning models or deep learning based architectures, CNN based architectures. They have not yet expanded it to machine learning models. I'm afraid, like, I don't know if they'll be doing it sooner or later. I think they are focusing on their computer vision and their Metropolis project. Uh, I think that's all for the questions. If anyone has any doubts or anything, you can reach out to me on LinkedIn. You can reach out to me using mail. I am available on both platforms, and I'll be happy to help you out understand TensorRT and Deepstream. Hello, Jatin. Oh, all right. I'll hang out in the launch if anyone wants to join, and I'll be happy to answer your questions. Sure, yeah. Thank you, Jatin, for being the host for this session, and thank you all for attending the session.